Hi everyone, welcome to another video of Intro to Machine Learning. In this video, I'm talking about support vector machines. Um, we'll discuss the mathematics behind support vector machines, not extremely detailed, but some part of it, of course. What are kernels and how they're used and why they're used. And then finally, we'll look at the Python implementation of support vector machines. Okay, so coming to the definition of support vector machines, it is a supervised machine learning technique that is mostly used for classification tasks but can be used for regression as well. It's used to classify higher dimensional data, and whenever we are dealing with higher dimensional data, as we shall see, we use something called kernel, and we use the kernel trick to represent data in higher dimensional spaces and find um, hyperplanes, or maybe think of it as a decision boundary that separates different classes. Okay, a lot of terminology there. We'll talk through the terminology one by one. Even before we begin, what is the fundamental idea? What is the intuition behind support vector machines? As you can see here, let us assume that we have two variables, two features, x1 and x2. If you remember the logistic regression lecture, in that video we talked about two different features. For example, the age of a customer and the salary of a customer, and based on that we were determining whether the person buys something or not. So let us assume this is representing that the customer purchased something, and this is representing that the customer did not purchase anything. Okay, the intuition behind support vector machines is that we need to find a plane, which in two-dimensional obviously is a line, right? But you can imagine that in a higher dimensional space, it is going to be a plane of certain dimension and so on. For this particular picture, it is obviously a line. So we have to come up with a line that separates these two classes of people who purchased versus classes of people who did not purchase. Because the purpose of any classification task is to have that separating boundary. So that when somebody, let's say, gives us a new point who has a salary and an age somewhere here, we are able to predict whether that person lies in this class or in this class. Okay, as you can see from this picture, there can be multiple ways of getting this separation, right? I can get this, or I can get another line here. Maybe that's not an exact way of representing it, but basically the idea is that I can get multiple hyperplanes that can separate these two classes. So our goal here is to find the best hyperplane. Something, for example, here, a plane or a line that maximizes the difference between these two classes, right? So sounds like a pretty vague idea, but even before we jump into how to get this maximum marginal classification possible, we look at something that's known as a hyperplane. As I said, in a two-dimensional space, a hyperplane is nothing but a line, but in the most generic format, we can represent any hyperplane using this equation, right? So let's say beta 0, beta 1, and so on are the parameters, and then beta 2, x2, and so on in a p-dimensional space is going to look something like this. So this is the equation of a hyperplane. Notice if beta 0 is 0, that means the equation, the hyperplane passes through the origin. Think about p equals 2. So you'll have only these two terms, which essentially are nothing but the equation of a line. Okay, the vector of all these parameters that essentially we need to determine whenever we are doing any machine learning task, right? So the vector of all these parameters is essentially, if you like mathematically, this is the normal vector and it points in a direction that's orthogonal or that is perpendicular or 90 degrees to the surface of the hyperplane that is represented by this equation. Okay, so this is the hyperplane, right? And the vector that comprises of all these parameters is orthogonal to the hyperplane. Okay, so let me see if I have more space here, right? So if I want to draw this hyperplane, let's say in some two-dimensional space, x1 and x2, let us assume this is my hyperplane. So essentially, this is the orthogonal vector that I'm talking about. This is the 90 degrees. This is my hyperplane, right? The normal vector that comprises of all hyperplane that comprises of all betas, beta 1, beta 2, and so for example in this one it will be beta 1 and beta 2 because it's just like two-dimensional, right? So let's say the data is something like this. This is the data. Some points lie on the hyperplane. So if you think about these points, each of these points can be represented using the equation of the function of the hyperplane. For instance, here, this particular point, let's say, can be represented as beta 1 times some x1 plus beta 2 times x2 plus some constant, which could be a number, or minus a constant equals to some number, let's say u. Okay. Similarly, this point here can also be represented in a similar way, beta 1 x1, beta 2 x2, plus some constant, if at all, equals some number v or minus v or negative, right? So the negative and the positive sign here represents which side of the hyperplane do these points lie. And one small thing, now this is the value of the function essentially. The value of the function is going to be some number. The value of the function at this point is going to be some number, which is my minus v and so on, right? So we can determine these values. And if this here is a unit vector, then each of these values, whether u or v, is nothing but the Euclidean distance of each of these points from the hyperplane. You can tell actually, right? So the projection of each of these points on my unit vector is nothing but actually the Euclidean distance from the hyperplane. But you can actually tell because look, this is the distance of each of these points from the hyperplane. So the projection, just remember the projection of each of these points is nothing but the actual Euclidean distance of this point from the hyperplane. So this was some fundamental idea about the hyperplane. So basically the equation of a hyperplane is given by is in this form, and we can determine the distance of any point from a hyperplane using this form. So this was a quick review of hyperplanes. I'm not going into further details. Let's go and check what are separating hyperplanes then, right? So let us assume if we are writing f of x as the equation of the hyperplane, right? So beta 1 x1, and depending on what is your feature space, you can just go on, right? So if let's say it is a p-dimensional space and so on, beta p xp, right? If this f of x is strictly greater than 0, right, for points on one side of this plane, and if f of x is strictly less than 0, then this will determine points on the other side of the plane. So think about this picture here. Let us assume these are the people who did not purchase. We can classify them as having negative outcome values. Outcome values are, let's say, yi's, right? So yi's are all negative. We'll say that these are all coded as negatives, and these are all coded as positives because it depends on which side of the hyperplane they lie. And this actually leads us to something called the maximal marginal classifier, which means amongst all separating hyperplanes, find the one that maximizes the biggest gap, which essentially leads us to this optimization problem. Maximize over all the betas, which is beta 0, beta 1, and like whatever beta we have, right? Maximize this margin subject to the unit vector that we had for all the planes, right? So beta j square equals 1. And the second most important constraint is whatever the outcome times the equation of the separating or like whatever hyperplane I1 plus and so on beta p x ip is greater than or equal to that margin. For all, I would also write that I equals 1 up to n, right? So this is nothing but a convex optimization problem, and the solution to this will lead us to the maximal separation here. The equation of the hyperplane that has these betas, like whatever the solution of this optimization problem is, that will lead us to the maximum separation between the two classes. Okay, so this was about the maximum marginal classifier, but this sometimes may lead to issues, right? Sometimes we might have non-separable data. For example, x1 and x2 looks like this, right? What happens if I have data like this? Because that was actually wishful thinking when we said we can separate data into two separate parts, right? That is not always the case. So this could happen at times, or we can have noisy data. What I mean by noisy data is, for instance, we have something like this, right? And we determine some classifier here, right? And then we want to determine or let's say there was another point here and the rest of the points were like clustered around here, right? And there was one point here. So based on this point, I'll have to like determine my classifier something like this. So just like one outlier sort of made my classification task like all of a sudden completely different, right? So these kind of scenarios lead us to the idea that this rigid margin that we talked about when we said maximum marginal classifier was not a really good idea, right? So instead of like, because of these issues that exist with that maximum marginal classifier, we come to something that's known as a support vector classifier. It's more like it has a soft margin. What that means is, let me show you in a picture, is that instead of having a rigid hyperplane, right, we decide to have a decision boundary and some soft margins around it, which essentially means, um, let's say this is my data, right? So this is one class and this is like another class. So what we do is we have the decision boundary just like we had for the maximal marginal classifier. But in addition to that, we have these soft margins. So just like, remember the terminology, these are margins and this is the decision boundary as it was earlier, right? So how are these margins decided? If you go back and look at this equation, right? I'm saying all of this, the outcome plus one or minus one times the equation of the hyperplane should be greater than or equal to this maximum marginal this maximum margin, right? What I can do is I can update this constraint and allow some slack to happen, not to have a rigid constraint, but to have some slack, which is like 1 minus epsilon I. Epsilon could be any value that's greater than 0. And also think of this as, depending on the number of points that we have, this epsilon I will have a certain budget. So this is constrained by a budget, which means we allow certain slack, which is determined by this parameter C. You can think of it as a regularization or a tuning parameter, because the higher the value of C, that means we are allowing more slack and we can have a larger margin, versus we can have a very narrow margin if the value of C is low, right? So based on this epsilon, the small slack that we have allowed, this margin becomes possible here, right? So we have this soft margin here, and this is our decision boundary. Now notice what can happen at times in this situation. You can have, now this is the margin, right? So we are hoping that all our data lies outside this tube or this margin, whatever this is, right? This is the width of this tube. Now notice there are certain points that are within the boundary, right? And then here also there are certain points that are within this soft margin, and even some points on the other side of the decision boundary, right? So this can happen, of course, and these will be like classified in the other class. But notice that these points are important. We actually, the epsilon is actually determined by these points that lie within the soft margin, because these are the epsilons. The distance of these points from their respective boundary are the epsilons. And the epsilons take different signs. For example, maybe this side it's a negative sign, the other side is a positive sign, and so on. So here we can tell that the points that are closer to the decision boundary, or maybe they're similar somewhat to the other class, they're very close to the other class, are the ones that are determining the size and the alignment of my decision boundary, or my soft, I would call it margin, right? So these points are really important, and these are the support vectors. So that's where the name comes from, because obviously you know that each of these points are nothing but vectors, and these are the support vectors because these are supporting this tube here, this tube of soft margin that has these like dotted lines, and then obviously the actual decision boundary. Okay, so this was about support vectors. This is the math behind support vectors. Um, a little bit about kernels. Now we've talked about data that is noisy, data that's mixed, data that is easily separable. But what about data like this? As you can see, this is not at all separable. And so in a situation like this, like let's say this is a two-dimensional space, one solution to that is to transform this into a three-dimensional space, as you can see, like bring these red points up and then have a decision point boundary of some one dimensional less than the transformation, right? So this is possible, and this is known as a kernel technique. Um, what can happen, what can go wrong here is that let's say my data wasn't two-dimensional, it was three-dimensional already, right? And then it was non-separable. And then to arrive at the condition like this, I'll have to go multiple higher orders in my dimension, which will make things complicated and less efficient. So in order to deal with that, we have something called kernels. Again, there's a lot of math involved here. I'm not going into the details of that because this is an intro course in machine learning. So I'll simply talk about these kernels because we will use them when we call scikit-learn. Okay, so when, as I said, there are more and more dimensions, computations within that space will become more expensive. And so we use kernel trick. So we do not do this transformation of higher dimension. Rather, what we do is we operate within the original feature space. And there's something called a kernel function that is utilized that does all the complicated computations for us in the higher dimensional space. If you're really interested in understanding this, what it essentially does, a kernel function, is that it it works within the original space by calculating the dot product of one of, like, let's say, features and the transpose of the other. So we do not work in the higher dimensional space anymore, right? Many different kernels are available. If you're simply interested in using them, then some of the most popular ones are the polynomial kernel, the radial basis function kernel, and so on. Right, so these are all available with the packages, whether you're working with R or whether you're working with Python. Okay, so this was all about support vector machines. Let's go and look at its application in Python. Okay, obviously I want to keep this. And okay, the data that I'm using and the problem that I'm looking at is again the same problem that we looked at with logistic regression. You have age of people and the estimated salary, and then this is whether they purchased an item or not, given that they were shown that item in an ad or in some other form. Okay, so this is the code. I'll provide that in the link in the explanation description below. So this is importing the libraries just like we've done before. So I'm not talking about that. This is importing the data set. We've done that. Train, test, split. Scaling is important. Feature scaling is important because when we are deciding the soft boundary here, always remember um, here when we are deciding the soft boundary here in this case, units count because the calculation all is done in like all of the features have the same level, or you can rather say that they all have the equal say, right? So scaling is important whenever we're doing support vector machines. So that's why I did scaling on my train set and test set as well, right? And then this is important. This is the added part here. And if you're not familiar, all I did was I just simply did a Google search on scikit SVC, and it takes me to this link. So here is the class, SVC class. Obviously, it takes a lot of parameters. We are not using all of them, but notice the value of C. This is usually given as 1. This is the regularization parameter that we talked about as a budget, right? How much margin we want, whether we want a greater margin, so give it a higher value, whether we want a lower margin, give it a smaller value. But mostly the default is 1. And this is what kind of kernel you want to use. If you go down and see here, these are the different kernels that are available to us. The default is radial basis function, which is RBF. So I'm using that. Okay. So this is how I import this class from the scikit-learn.svm library and then create an instance of that class. Notice I'm using RBF, and random state equals 0 will help me get the same results every time I run it. Okay. This you might remember from one of the previous lectures. Once we've created the classifier, this is how we predict it. Just do a dot predict and then do a transform on that. And here I'm going to get the test and the train, the test values and the predicted values, and then see how many have not been predicted. And even a better way of looking at it is to get the accuracy score and the confusion matrix. All of this code was already provided to you in the logistic regression lecture. So the only thing that's new is this one. Okay, If you remember, the accuracy score in the logistic regression model was 89.89. So let's see with the same problem, with the same data set, what is the accuracy score that we get here. Okay, let me run this. Okay, so as you can see, the accuracy is higher in this case. So obviously for some problems, support vector machines work way better than logistic regression. So this is one instance of that. So 93%, way higher than 0.89. And as you can see here, the predicted versus the actual, most of them look good to me. A summary is here in the confusion matrix, right? So how many were actually true and how many were predicted true and how many were actually false, how many predicted false. So all of that's there. I've provided the code and the link to the data in the description box below. So that's all about support vector machines. Thank you. And if you have any questions, please ask in the comments.